Okay, so let's get started. Hello everyone, this is Zhendong Wang, and I'm a PhD student at the Data Science Group at Stockholm University. And this is my presentation for Learning Time Series Counterfactuals via Latent Space Representations. And this is a joint work together with Isaac Samistan, Rami Mocharab, and Panagutis Papapetrou. Here is my email address. If you have any question or if you have any suggestion after my presentation, you're welcome to contact me. Okay, so let's start by talking about time series classification. So as many of you already knew, in recent years, there has been many machine learning algorithms proposed, such as elastic distance measures, intervals, shapelets, and also there are some SOTA breaking through methods, such as inception time, rocket, and it is different from traditional machine learning classification. This is due to the feature dependency of the ordered data at a different time step. However, many of those methods are considered as black boxes, so they lack this model transparency and prediction interpretability. But in reality, many application areas require such model transparency to gain the user trust and the reliability. This creates a nice bridge to our approach, which is counterfactual explanations. So by definition, this is an example-based approach in explainable machine learning, and it shows modifications required at different features to change a prediction from an undesired to a desired state. So in this case, we can see from the right, there is a nice figure illustrating there is a time series counterfactual. So the blue line here is the original ECG, and this red one is this counterfactual. So we can observe that there are some feature value changes, also this shape here and the peak values. So by offering such change, we provide like information of how to convert from abnormal ECG to a normal ECG. This is a counterfactual. And now you may wonder what's going under hood of this counterfactual solution. So here we have one figure illustrating this problem under the hood. So we have a binary classification problem. So to the left, we have this positive and we have this negative class. And there's a nice curvy decision boundary drawn in the middle. So imagine that we have an original point X, and then we try to find the path A and path B to cross this decision boundary to get to this counterfactual CF1 and CF2. And both of them, they are considered as valid counterfactuals by crossing this decision boundary. And yeah, now we can talk about some pros of counterfactual explanations. So firstly, it provides actionability, which is complementary to explainability. And a simple notion could be that if feature xi was modified or was changed, then the output y would be changed to the desired target class. And secondly, it's a model agnostic, so it's suitable for explaining any black box machine learning model. And finally, if we looking at these counterfactuals, the domain expert can get a better understanding of the decision boundary without really explicitly opening the black box. But also they can obtain direct insights on how to alter these predictions to another target class. Okay, so let's talk about some related work. So talking about this time series counterfactual, current state-of-the-art method is this RSF time series tweaking approach. So this RSF method focused on minimizing two metrics, compactness and cost. And however, in our observation, we found that the method often failed to generate counterfactuals that are compliant with the underlying data distribution. So on the other hand, we can find these counterfactual generations by using latent space. So some methods using auto-encoder and variational auto-encoders. However, those methods only focused on tabular or image data. And to the best of our knowledge, it has been generalized to time series domain. And also we observed this LatentCF, which is like the method we are trying to follow and extend. They often failed to generate valid counterfactuals due to this inefficient generation. We will talk about their approach in 2 slides. And so given all the background information of counterfactual and time series classification, there is a list of our contributions. So firstly, we formulate this univariate time series counterfactual problem and providing a novel solution, LatentCF++, by employing this latent representation. And we demonstrate 2 model instantiations of LatentCF++, and where we applied both CANs and LSTMs, together with a model extension of a composite autoencoder. And thirdly, we conduct an extensive experiment in terms of real-world data using the UCR archive. So we compared with some other baseline methods, and also we achieved comparable performance in terms of proximity with the current state of the art. And we will talk about these 3 different evaluation metrics in our next slides. So now we want to understand what is actually this problem. And given any classifier F and a time series sample X, so that this original classification was a negative one with probability of y hat. And our goal is to utilize an autoencoder to use this encoding function and the decoding function to find this counterfactual with the desired positive outcome. And our solution is that what we actually trying to do is to perturb this encoded representation Z using this encoding function through a gradient descent approach iteratively to generate a new time series sample X prime with this target class. And here is an illustration of the method we are trying to follow and extend. So this was a method called LatentCF, and here is this flow chart of how they convert, how they transform MNIST handwritten digits from number 4 to number 9. So we can see that there is an encoder and decoder, and there is this classifier. So firstly, what they do is to use this encoding function to get this original image into this latent space Z, and then they using decode and use this classifier to get this prediction probability, and then they compare to get this loss, and then making use of this loss information, they try to update this latent space Z iteratively using the gradient descent, and until they get this target output, which is a number 9 in this case. So here is our solution of LatentCF++ in time series counterfactual. So we can see that we have input of time series X, time series sample X, then with a bunch of different hyperparameters. And so in the beginning, we are taking an input of X, and then we encode it to this latent space Z, and then we decode it, and then we predicted it to this y pred, which is the same as y hat, and then we use MMSE function to measure the loss, and then following the next, we do this iterative gradient descent update using this Adam optimization. So after that, we decode and predict and measure how is the loss iteratively through this while loop. And by the end of this function, by the end of this algorithm, we generate a new time series sample X prime using this decoder. So our improvements here is that firstly, we integrate this Adam optimization, which can make the counterfactual generation process more robust, and also it has more efficient generation process. And on the other hand, we add extra constraints in line 5 here, so to improve the validity of generated counterfactuals. And talking about our experiment, the data is from this UCR time series archive. So after filtering, we have a subset of 40 different datasets and with binary classification problems. And to the right, we can see some example datasets from this UCR archive and some of this information. And the time series length varies from 24 to 2,709 time steps. Also, we applied a standard split up of 80-20 for training and test to facilitate our deep learning model training process. And our implementation code are publicly available at this GitHub repo. Also, our full results are available there if you want to have a look. Okay, so after talking about the data and setup, now we're talking about the model part. We have some model instantiations from our proposed solution. So we can see that there are 3 different instantiations. One is 1DCN LSTM and 1DCN-C from our proposed LatentCF++. And this 1DCN-C stands for a composite auto-encoder, which is one extension from those 2 instantiations. And also we have the same instantiation for this original LatentCF method. So take the first instantiation as an example. We can see it's composed of this 1DCN autoencoder and another 1DCN classifier, together with this Adam optimization and this boundary threshold of 0.5. And the same goes for the rest. So yeah, so now it's getting to the interesting part. We want to talk about the results, but before that, let's look at the metrics first. So firstly, let's talk about the validity. Validity is our main metric for our experiment evaluation. So it's reporting this fraction of valid counterfactuals. So here we have this count of these counterfactuals that have been crossed this boundary, and which is divided by the total amount. And secondly, we have this margin difference proposed. So this is simply to measure how close is the prediction probability of the generated counterfactual compared to this boundary tau. And next we have this proximity, which is to measure the feature-wise distance between the generated counterfactuals and the original samples. And this is simply defined as this distance metric here. So in our experiment, we use Euclidean distance for reporting the proximity. Okay, so let's firstly look at this validity table of 5 different datasets from our experiment. And in the actual paper, we reported 20 different datasets. And here, due to the limitation of the slides, so we only report the top 5. And we can see the best score for each dataset is highlighted with this dashed line. And if we compare across these 5 datasets, we can see actually this RSF, which the current state of the art, achieved 100% validity. But our proposed solution, this 1DCN for LatentCF++, achieved the 3 of like 100% validity, and the rest 2 has very close to 1. But if we look at the average score across all 40 different datasets, we can see that our 1DCN instantiation actually achieved the best, and the RSF achieved the second best with 0.98. And the next one, we look at this margin difference. So we can see this subset of 5 different datasets. And note that this metric here could be negative because it could be to the left of the design boundary, which means it's not a successful transformation for this counterfactual. So additionally, we reported this standard deviation of this score across all the datasets. Actually, in this case, our proposed solution, LatentCF++, outperform the other different baseline methods in this case. And if we also look at this average score and the standard deviation, we can see that it also achieved the best performance among all of them. So this suggests that our counterfactual is very close to this decision boundary, so which can infer to a more efficient generation, also with less perturbations in the latent space. And this is a summary of proximity score. So we can see that the 3 different methods are excluded in this comparison because they have low validity, and because validity is our main metric. So for the rest of those 5 different methods, we can see for these 5 different datasets, 3 of the winners are from this 1DCN method, and 2 of them are from this RSF. But if we look across all 40 datasets, actually LatentCF outperformed in 17 of 40, and the RSF outperformed in 21 of them. But also this can be reflected in this average score. We can see the best one is performed by RSF, while our solution achieved the second best. And this suggests that our approach can generate counterfactuals that are close to the original samples in the competitive manner. And now this is an interesting example of the individual ECG data. So we can see that here we have three different models. We have 1D-CNN from LatentCF++, and we have LSTM, we have RSF, and we can see actually 1D-CNN and RSF, they achieved similar transformations in this case. But if we look closer, we can see actually 1D-CNN appeared to be more smoother transformations, while RSF has a bit more like bumpy transformation. And this is due to that we actually use this auto-encoder to find the underlying data distribution, but RSF is not optimizing for it. So it's taking the feature space directly for this transformation. And if we look at this LSTM model, we can see that there are several parts. Actually, it poorly aligned with the original time series, and also it diverged in some many time steps. So we can see this LSTM doesn't perform like very robust transformations in this case. Okay, to move on to our final point, and here is a quick summary of our paper. So firstly, we present this counterfactual explanation framework called LatentCF++ for time series counterfactuals. Also, we showed the generalizability of our framework using a unified set of deep learning models. Another recap is that our experiment suggests that our method outperformed the other baseline models in terms of validity and the margin difference. Also, it achieved proximity, comparable proximity compared to the state of the art. And so for the future work, as you might have noticed, this LatentCF++ framework is quite general, so it can be extended into more different types of data, such as textual data and tabular data. So we are planning to extend our work to generalize it for broader problems. Also, we intend to conduct a qualitative analysis from domain expert to validate our results to see if they are actually meaningful in different domains. And here are the list of references. And thank you so much for your attention. And if you have any questions, I'll be happy to answer them.